Good afternoon, everyone. I think we are ready to begin for the new session. And now we have a change of topics. And we're beginning now today with the interesting part of planet formation after we have heard so much about star formation. But we heard a lot about the transition to planets already today in the morning. And I hand over to Anders Johansen, who will talk about the multifaceted planetesimal formation process. Anders, please.
Okay, thank you, Willy, and good afternoon, everyone. I'm delighted to be here today to present the review chapter on the multifaceted planetesimal formation process on behalf of the author team, which, aside from myself, consists of Jürgen Blum, Hidekazu Tanaka, Chris Ormel, Martin Bizarro, and Hans Rickman. So I'd like to start by motivate why we care about planetesimal formation. Well, of course, we care about planetesimals because these are believed to be the building blocks of both the terrestrial planets and also the cores of the gas giants and the ice giants. So the planet formation process takes us over a staggering 13 orders of magnitude from the originally micrometer-sized dust and ice particles all the way up to fully fledged planets. And actually, the planetesimal formation stage is a significant part of this growth because one can broadly define the planetesimal formation stage as a stage from micrometer-sized dust until sizes which can undergo runaway accretion. And this depends a little bit on the background turbulence, can be anywhere between 1 and 1,000 kilometers. And what defines then the planetesimal formation stage when it comes to physical processes is that we don't have any gravitational focusing, right? We cannot have two bodies gravitationally focusing each other. That means that particles must now grow either by sticking or by a collective gravity. So not two-body gravity, but a collective gravity. Now, we are so fortunate, actually, that not all planetesimals turn into planets. So nature has provided plenty of planetesimals which are left over from the planet formation process, both in the solar system, where we have the asteroid belt and the Kuiper belt, and also around other stars, where we have the debris disks. So starting in our own solar system, the asteroid belt is continuously sending down rocks down to Earth so that we can study them. And by looking inside of those meteorites, one can, for example, find CAIs, calcium aluminum rich inclusions, which can be dated very carefully with long-lived radionuclides to have a narrow age range of 4, 5, 6, 7.30 plus minus 0.16 million years. This is how old the CAIs are. And this is normally used then as a t equal to 0 of the solar system. This is when the solar system formed, we say by definition. Now, primitive meteorite parent bodies also contain a large fraction of 0.1 to 1 millimeter sized chondrules. So we have two examples of chondrules here. And they actually started forming at the same time as the CAIs, so around 4, 5, 6, 7 million years ago. But then they formed over a much longer time span, up to 2.5, 3 million years after the CAIs. So even we know that some meteorites are not primitive, they come from differentiated parent bodies, and that means that some large parent bodies of the meteorites actually differentiated, presumably by the decay of aluminum-26, which was active in the early solar system, and this must have happened less than 1.5 million years after the CAIs, and then after it's believed that the primitive parent bodies, which contain all of this stuff, then actually formed after the decay of aluminum-26 did not make it possible to differentiate anymore. If we turn our attention to other stars, we have the debris disk, which we already heard a review talk about today. And I think an important finding about debris disk is they're very common. This is just a plot from the Ziegler et al. Paper here, which is the data from Spitzer, showing as a function of the age of the cluster, what is the fraction of debris disk. And this line here shows for solar type stars is A and B stars. And whatever the percentage is here, it's rather high, so we can say that at least 30% of young FGK stars have detectable debris belts, and that it goes up with decreasing age. So what I'm trying to get at here is that nature is telling us that planetesimal formation is universal. It happens around all stars. And it's also rapid in that large planetesimals which can differentiate must form within maybe 1 or 2 million years. Good. So what happened since the last Protostars and Planets review in 2007? Well, we can parameterize this in terms of this equation here. I think this is probably the only equation I'm going to show. But this equation is a form of the Coagulation Equation. I'm basically showing here if I'm a particle of type I, what is the flux of the red particles of type J onto me? And this is, of course, just equal to the cross-section times the density of the red particles times the relative speed. And when I have an m dot here, I don't mean actually the growth rate of particle I just mean the mass flux. Some of these particles may not actually stick, they may bounce, or they may actually fragment a particle I. But we can use this equation here to show where there has been major progress made since the last Protostars and Planets review by Dominic et al. In 2007. And I'm listing here 4 areas where we have identified major progress and which we focus on in our review. And the first is simply on the collision outcome. It's not in the equation, but it's about this idea about whether the m dot here leads to mass growth or just bouncing or fragmentation. And actually there's some progress on the collision outcome here that you can have a mass transfer and sticking at a very high relative speed. Then there's also been progress made on the collisional cross-sections that you could have fluffy ice aggregates, extremely fluffy ice aggregates with very large cross-sections that can boost the growth of planetesimals very strongly. And there's also progress made on the density environment here, the rho J, that actually particles are not uniformly present in the protoplanetary disk, but rather they are concentrated in pressure bombs, in vortices, and by streaming instabilities. And finally, this last term here, the relative collision speed, there's actually also some new realizations that the gravitational torque from turbulent density fluctuations is important for determining the collision speed. So I'm going to go through all of these 4 points now in a little bit of a reversed order. I'm going to start with point 4, and go through point 1, 2, and 3. And then in the end, I'm going to be so bold as to propose a unified model of planetesimal formation, which involves a little bit of all of this. Okay, so going now to point number 4 first, the collision speed. This is actually one of the areas where it's become harder to be a pre-planetesimal since the last Protostars and Planets review, and I'm going to show you why. But in order to understand collision speeds, we need to talk a little bit about non-dimensional numbers, which theories like so much. And one important non-dimensional number in a protoplanetary disk is the so-called Stokes number. The Stokes number is a measure of the so-called friction time, so particles react to the gas on the friction time. A complicated expression that depends on particle size, speed, local gas density, and so on. But it turns out you don't have to worry so much about friction time, that the important number is the so-called Stokes number, which is the Capillarian frequency times the friction time. And many aspects of particle dynamics, actually sedimentation, collision speeds, radial drift concentration, are actually determined only by the Stokes number. And then when you find a solution for a given Stokes number, then you can reverse engineer and go back and find out what was the particle size corresponding to that Stokes number. That's what I've done here. As a function of the semi-major axis here, we see the particle size corresponding to a given Stokes number, 0.01, 0.1, and 1. Just highlighting Stokes number 1 particles are approximately a meter in size in the inner disk within a few AU. And then when you go out in the outer disk, they go down to a few centimeters in size. This is for an internal particle density of 1 gram per cubic centimeter. You can also do 10 to minus 5 grams per cubic centimeter. That sounds really peculiar. Why would you choose something so fluffy? But I'm going to show you later that particles may actually be that fluffy. And then the Stokes number 1 particles are actually 1 kilometer in size in the outer disk, and even up to 10 or 100 kilometer sizes in the inner disk. I should just warn you here that sometimes the Stokes number is based on the frequency of the smallest edit omega, so this is a small-scale Stokes number, but actually this large-scale Stokes number is the one that I would say is the most important one for the dynamics in protoplanetary disks. So one effect that is determined by the Stokes number is what Leonardo Testi talked about yesterday, is the radial drift. It simply is caused by the fact that the gas in the protoplanetary disk is slightly pressure supported in the radial direction, and makes the gas orbit slower than Capillarian by an amount of approximately 50 meters per second, relatively independent of R in the Hayashi Nebula. And the particles then face a headwind from the slower moving gas, and they drift towards the star following this expression here, where we see again the Stokes number here, not the friction time, not the particle size, but the Stokes number. Stokes plus Stokes inverse, it has to peak somewhere at Stokes number 1, and that's also what we see here at 5 AU, minimum mass solar nebula. At 30 centimeters, it peaks at around 50 meters per second, and then goes down on both sides for smaller particles and for larger particles. And this is the radial drift barrier, which people talk a lot about, that the drift time scale is only 500 years for particles of 30 centimeter radius at 5 AU. So we need to grow past this drift barrier before the particles drift in towards the star. Right, so now I'm coming to the point of new progress, and that has to do with the collision speeds. So the collision speed of particles is excited by Brownian motion, differential drift, gas turbulence, and turbulent density fluctuations. And this is a classical study of planetesimal formation. What is the collision speed between particles of 2 different sizes? A Brownian motion and the differential drift, there are analytical expressions which one can use. For the gas turbulence, this is a bit hard. One has to parameterize basically the eddies in the Kolmogorov cascade, and this was done first by Filament in 1980, and also followed up by Weidenschilling and Coetzee in 1993. And one relatively recent development is that Ormel and Coetzee actually derived some very nice closed-form analytical expression that makes it very easy to calculate this relative speed. So this is a classical representation of the collision speed, particle 1 size, particle 2 size, meters here. And we see here that small particles, this is the collision speed in meters per second, small particles collide at low speeds, we go higher and higher, and particle size, they decouple from the smallest eddies, collide at higher and higher speeds. We go to even larger particle sizes. So this is Stokes number 1, where we have the highest speed. We go to even larger particles, and they decouple from the largest eddies, and then they start to collide at the smaller speeds again. And if we go down from alpha of 10 to minus 2 to 10 to minus 4, we have a weaker turbulence, then you can see that we actually get much lower collision speed, 10 meters per second, and even up here down 2.1 meters per second. However, we need to revise this, and that's what we are proposing in our review also, because the contribution from turbulent density fluctuations is not included here, it's included here. This effect was parameterized by Ida et al. 2008 based on the realization that turbulent gas is not also has density fluctuations, and the gravitational torque from those density fluctuations can give significant eccentricities and collision speeds. This is actually inspired by simulations of stochastic planet migration, but then applied to smaller bodies. If we apply this using some analytical fit to the turbulent density fluctuations, then we can see a whole different picture here. It looks the same down here. Go to larger particles, this oasis here vanishes completely, and the collision speed just rises and rises and rises. 100 meters per second, 200 meters per second, higher and higher. It helps if you have a little bit of a lower alpha, of course, because alpha also controls the turbulent density fluctuations, but still this oasis up here with low collision speeds becomes lower, and then it actually vanishes when we go up further. And this is very important because this allows us to define now the planetesimal formation stage as the time during which we don't have any gravitational focusing, and that depends then on the amount of turbulent stirring. You can see here basically the turbulent collision speed here as a function of the dust particle size based on calculations by Okusumi and Ormel and Okusumi. And you can see here we have the first peak in particle collision speeds around Stokes number 1. These are the 30 centimeter sized particles. Then it goes down again. Just focus on this line here. This is if we have fully developed MRI turbulence. Then it goes down, and then the gravitational torques take over here beyond 100 meters, and we get really high collision speeds. And the only point at which the escape speed catches up with the collision speed is when you're 1,000 kilometers in size. So in this case, it's not enough to say, aha, I have a 1 kilometer sized planetesimal, because it would never survive, it would undergo fragmentation, and it would also not be able to undergo runaway focusing. You would have to go up to 1,000 kilometers in size. Now, as we heard yesterday, of course, this ideal MRI situation is maybe a little bit outdated now. We maybe believe more that there's a huge dead zone and that maybe disk winds are driving the angular momentum transport. So one can parameterize what happens inside a dead zone in this plot here. By the way, the two lines are 1AU and 5AU, 1AU, 5AU. Inside of a dead zone here, it gets a little bit better. So we have the peak here, and we have the valley here, and then we get the turbulent density fluctuations. But even in this case, you can see we need to grow to planetesimals that are somewhere between kilometers or 10 kilometers in size before we can undergo runaway accretion. So this is just making the point that the extent of the planetesimal formation stage actually depends on the amount of background stirring. Yeah. Okay, so that was the bad news in a way for pre-planetesimals now, that the collision speed that we believe today for 100 meter or kilometer sized bodies are larger is actually much higher than was thought 10 years ago. But now I'm going to go through some effects that can lead to growth and which can possibly overcome this kind of problem with the high collision speeds. Okay, so first of all, I'm going to talk a little bit about the collision outcome. So in a way, if you want to form planetesimals, basically the goal of planetesimal formation modeling is to find a particle size distribution as a function of time and semi-major axis. What particle size do we have, when and where? You can take the density environment from the minimum mass solar nebula or from hydrodynamical simulations with particle concentration. I'm going to come back to this point. And then you can take the collision outcomes from experiments. Leonardo already talked about this yesterday. I'm not going to go through it very much. I'm just going to mention that there are lots of experiments done in different laboratories in the world on what happens when you collide particles with different sizes, different porosities. What is the outcome? This is just a nice plot here from the Goodlad et al. Paper, which shows the outcome of various kind of collisions. And there's another plot in this paper also where you can say at what speed does what happen after the collision. Now, a final point here is actually that you also need a way to calculate the collision frequencies, and you need some kind of particle interaction model, some way to solve the coagulation equation. And here there's also been done some major progress in the last years, particularly using Monte Carlo models, which can track not only the size distribution, but also additional properties such as porosity. I'm showing here an example of such a Monte Carlo simulation here by Stokes Number, where he is tracking the mass here as a function of time, and here he's tracking the porosity as a function of time. And we can see we start here, okay, this is in mass, but this is approximately micrometer-sized grains. They grow because the blue line goes up here, right? And then they grow to a certain point, and then they kind of settle down around millimeter sizes. And you see at the same time that the porosity develops. First you don't have any porosity, then you have a rather high porosity, and then you come to the bouncing barrier actually, that these particles start to bounce off each other, they start to compactify each other, and once they bounce then they don't stick anymore, they become compact again, and you end up with a lot of millimeter-sized particles that don't grow very much larger. This is the famous bouncing barrier that Leonardo also talked about yesterday. But there are reasons to believe that the bouncing barrier is not the end of planetesimal formation. And one way to get around the bouncing barrier is by the so-called effect of mass transfer. So the mass transfer effect was pioneered by Wurm et al. In 2005. And they basically collided a small projectile with a large target at higher and higher speed. So they go here below 10 meters per second. This is the accretion efficiency, how much sticks to the target. And we see not very much, maybe 5–10%, that's not very efficient. But if we go above approximately 10 meters per second, suddenly 50% of the projectile sticks to the target. It's a little bit like throwing a snowball at a wall. The snowball shatters and falls down, but a part of the snowball sticks to the wall. And if you then continue to throw snowballs at that wall, then you can make a layer of ice, which is actually very thick. So some mass will stick, up to 50% in sticking efficiency, above 10 meters per second. The big question here is, can you do this continuously? And yes, you can. I can just show you in a movie here. This is from a paper by Coagulation et al. 2010. They basically have a dust target here, and then they shoot little projectiles at the target continuously. And what you're going to see is that you can have a continuous growth. You form a cone, so you basically get mass transfer on top of mass transfer. And this way you can actually build up larger particles just by splattering small particles onto a target. Yeah. So the effect of this mass transfer was considered in this paper by Frederik Windmark et al. In 2012. And if you just focus on this plot here, basically Frederik solves the coagulation equation, including bouncing and mass transfer. Focus for now on the red line here. The red line here shows the bouncing barrier. This is the grain size. And this is at a certain time where the size distribution doesn't evolve anymore. The grain size is stuck here at around 0.01 to 1 millimeter. This is bouncing barrier that Stokes Number also found. But then Frederik does a little bit of a trick. He seeds artificially some centimeter-sized particles into this bouncing barrier, and then you're going to have the mass transfer. The centimeter-sized particles can grow by the millimeter-sized particles splattering onto them, and this way they can continue to grow with time. So you see this later and later, and you get actually all the way up to 100 meters in 10 to 6 years. Yeah. So this seems to be very efficient, that particles can grow by this mass transfer to 100 meters in 10 to 6 years. Just some of them are a little bit bigger than this bouncing barrier. Okay. Now the problem, as you may have noticed here, is that it's quite slow. Growth is much slower than the radial drift. It takes approximately 10 to 5 years to grow across the meter barrier. So that's from 1 to 10 meters here. It takes like 10 to 5 years, but the radial drift took only like 1,000 years. So it's like 100 times slower than the radial drift. We also realized this in a paper from 2008, where we modeled a little bit of a different system, which is a coagulation equation, which is a coagulation fragmentation problem, where large particles in the midplane are making fragments when they collide and the fragments are in turn sticking with other large particles. And the problem is that the large particles in the midplane, they make fragments, and then they get spread by the turbulent diffusion all over the entire column of the disk, and this way it reduces the sweep-up rate of the larger particles, which are still residing in the midplane here. So growth is much slower than radial drift, and it may be necessary to add pressure bombs. So that's a point that I'm going to return to. Okay. The next point of major progress since the last Protostars and Planets review, the collision cross-section. Because bouncing may not occur at all if the particles are porous enough. So if the filling factor phi of the particle is low enough, you may not have any bouncing, you may have sticking instead. And these are 3 different particle aggregates which have been assembled by Ward et al. 2011 in a computer. One with a filling factor of 0.74, one with 0.59, and one with 0.28. And numerical simulations indicate that the bouncing conditions, this phi should be larger than 0.4. So this one will bounce, and this one will bounce, but this one might stick to another particle. And this has also been confirmed in experiments, although that's a little bit of a disagreement between the actual threshold here. What there is agreement on is that fluffy aggregates would have a filling factor less than 0.1. They can stick at high relative speeds, both in numerical simulation and experiments. It's simply due to the fact that you have more internal degrees of freedom in a fluffy aggregate where you can dissipate energy, right? So Water et al. 2009, they found actually a sticking threshold for ice made out for fluffy aggregates consisting of 0.1 micrometer ice monomers of 60 meters per second. So you can stick it up to 60 meters per second. And if you apply this to silicates instead, you get 6 meters per second, so you see a factor of 10 comes from the fact that ice is more sticky than the silicates. I can show you a movie which Carlo gave me, which is right nice. This is a small fluffy grain colliding with a large one at approximately 90 meters per second. And you see? No fracturing, just kind of penetrating and sticking. We can also do it a little bit of an offset collision. That's a little bit more dangerous and a little bit more damaging. But still it goes around. And even 90 meters per second, you actually experience to have sticking. Yeah. So this was also put into a coagulation equation solver. This was done by Okuzumi et al. 2012. And they basically included now fluffy ice aggregates, and they use the fact that these should maintain a fractal dimension of 2.5 when they collide and stick. And if you have such a low fractal dimension, it means the bigger you are, the more massive you are, also the lower internal density you have, and then you get a huge cross-section. So this is the result of their simulations. Semi-major axis, aggregate mass, they started at micrometer sizes, which is something here in terms of the grams. And then they grow up in the inner disk. You can see the radial drift. And at some point, they cross this radial drift barrier here with the line, and they grow up and actually form planetesimals. And one reason you could do this is showed here. This is the internal density as a function of the aggregate mass. So you have here in the beginning, it's 1 gram per cubic centimeter. But as the aggregates collide and stick together, they become more and more fluffy, containing this fractal dimension of 2.5, reaching an internal density of 10 to minus 5 grams per cubic centimeter. Which they maintain then, this actually also when they cross the radial drift barrier, which is here at Stokes number 1, at this point, the particle is 1 kilometer in size. So it's a big fluffy ice particle, basically, which is crossing the meter-sized barrier. And one should also mention here quickly, actually, that the reason it's possible to cross the radial drift barrier is because the fluffy particles are in the Stokes drag force regime, where the Stokes number is proportional to r squared. And there are still some open issues with this. One is the question about compactification due to gas drag and self-gravity, particularly when the particles become kilometer size or larger. And there's a paper about this by Carlo et al. 2013. And if you want to know more about this, I invite you to see the poster here by Archimaster Carlo. Okay, so the third area of major progress since the last Protostars and Planets review is on understanding the background particle density. Because it turns out that particles are not uniformly distributed in the disk. Actually, they undergo concentration on many, many scales. Basically, one can identify 3 main concentration mechanisms in a protoplanetary disk, which are also illustrated here. The first mechanism is when you concentrate particles between small-scale, low-pressure eddies. And this is most efficient when the length scale is about the smallest scales of the turbulence, which is about 1 kilometer in kind of nominal protoplanetary disk. And you can concentrate particles of Stokes number between 10 to minus 5 and 10 to minus 4. So you concentrate here between particles. This was a mechanism that was proposed to work in protoplanetary disk by Jeff Cossi et al. In 2001, basically. If you go to much larger scales, you can have pressure bumps. And pressure bumps can be over a very large length scale from 1 scale height, maybe up to 10 scale height. So the full scale of the protoplanetary disk. These pressure bumps can trap particles with Stokes numbers between 0.1 and 10. And there's a third mechanism that also, I should mention, by the way, I say pressure bumps / vortices. And what I'm thinking about is this is a pressure bump with a supercapillary flow on the inside and a subcapillary flow on the outside. And if you want to turn it into a vortex, you just make it very elongated and you turn the flow around somewhere. And it's the same kind of effect. That's why I group together vortices and pressure bumps. A third effect here is the so-called streaming instability, whereby particles are, this arrow here shows the subcapillary flow of the gas, and particles can locally cluster and accelerate the gas more towards the capillary speed and thereby concentrate particles. I'm gonna go through these 2 effects now in a little bit more detail. I'm not gonna talk too much about this first effect. Let me go into a little bit more detail about pressure bumps and zonal flows. So basically, pressure bumps can exist on the largest scale of the protoplanetary disk in a balance between the pressure, which is pushing the bump out, and the zonal flow, so supercapillarian on the inside, subcapillarian on the outside, and the Coriolis force from this flow is going to push the gas back in. This is a perfect eustrophic balance. And actually, this kind of pressure bumps can trap particles because the particles here are going to feel a headwind from the gas. and move in towards the star, and here they're going to feel a tailwind which is going to push them out. The particles get concentrated here. And one way to make pressure bumps is actually by having a large-scale variation in the alpha value in magnetorotational turbulence. This is shown, for example, here, so this large-scale variation in the alpha value means you have a differential transport of angular momentum that makes a zonal flow. It makes a pressure bump. And the pressure bump can concentrate particles. That's what we're seeing here, basically. A simulation by Lyra et al. 2008, a global disk simulation with, and you see here the gas density has some variation by a few percent, and the dust density, on the other hand, has very large variations, and you can even see a bit of a correlation between the high density here and high density here. This becomes more clear now if we average over the azimuthal direction and stack up this information in time, then we can get a space-time plot. This is the so to say distance from the star, and this is time. And you can see at any time we go here, we can see, okay, there's a high pressure here and a low pressure here at 10 orbital times, and at this time here there's a low pressure here and a high pressure here. And now we can also inject particles into this flow, and you can see what happens when we inject particles here at a time of 32 orbits. We inject the particles, and they immediately concentrate a little bit downstream in this pressure bump here. So we can get some very large particle concentrations in pressure bumps. And this can, of course, be very, very good for planetesimal formation, because these regions can become gravitationally unstable, and then you can form planetesimals this way. I should say quickly that the final scale of these zonal flows and pressure bumps is still not quite known in the local box simulations. They always seem to fill the larger scale of the box, so one probably has to go to very large boxes or to global simulations. If you want to know more about the scale of zonal flows and pressure bumps, you can see the poster by Carsten Dietrich. Okay, so the streaming instability is very different. With the streaming instability, the particles take the active role in the concentration, and they do this by this sketch, which I'm showing here, of how the streaming instability operates. We look at a protoplanetary disk from the top, and here we have a gas fluid element, so to say, which is orbiting subcapillarian v kept times 1 minus eta, eta being a small positive number. And it does that, of course, because there's a gravity, and then there's a little bit of a contribution from a radial pressure gradient, because the gas disk is hotter and denser on the inside and colder and less dense on the outside. This leads to radial drift, as I explained. That I have an isolated pebble here. It wants to orbit capillarian. It doesn't feel the pressure gradient. It faces the headwind of the slower moving gas, and that makes it spiral in towards the star in a few thousand years. Now, the essence of the streaming instability is that if you can concentrate a few more particles at a certain radial distance from the star, then they can locally accelerate the gas speed towards the capillarian speed because of their drag force. That means that there's no headwind here. That means that this clump doesn't drift so fast anymore. And this is then a runaway process whereby an isolated particle here, pebble, becomes incorporated into the clump by its radial drift, and then it adds mass to the clump, which adds to the ability of the clump to trap more particles. So it's a runaway process. We modeled this in this paper from 2007, in its both in the linear and in its non-linear stage here. And these are 4 times here, and this is the radial distance from the center of the box and the vertical distance. And you should imagine the star being in here somewhere as a local co-rotating box. And we see the linear evolution of the streaming instability here, and then it goes even into a nonlinear phase, and even into a very nonlinear phase where dense particle filaments interact with each other in a complicated way. Now, one thing we should say about the streaming instability is actually that you need a particle concentration. In order to get particle concentration, you need to it gets triggered above a threshold metallicity, which can be a little bit higher than the solar metallicity. It depends on the radial pressure support, especially what was discovered by Barr and Stone 2010b. That if you have normal radial pressure support, you might have to go to 2 times the solar metallicity to trigger the streaming instability, maybe by particle pileups, maybe by removing gas. But if you go to a lower radial pressure support, actually you can get the streaming instability already at solar metallicity. Another question, an open question with the streaming instability is what are the smallest particles that can be concentrated this way? And actually, Daniel Carrera, who is a PhD student in Lund, he's currently studying how small particles you can concentrate with the streaming instability. And he's finding that actually it is possible to concentrate all the way down to millimeter-sized particles and 3 AU. And this may actually explain why we find chondrules in primitive meteorites. But I'm not going to explain this plot. I'm just going to invite you to visit Daniel Carrera's poster if you want to know more about streaming instabilities with small particles. Okay. So I talked a little bit about pressure bumps and about streaming instabilities, but I think one of the real strengths of particle concentration models now is that there are so many Right? There are so many models that have been proposed for particle concentration during this last decade that if one is a Stokes number 1 particle, so one would see a protoplanetary disk this way with lots and lots and lots of regions to concentrate in. It's not just a matter of a little peculiar effect that could happen somewhere here or somewhere here. There are many, many, many kinds of effects that can concentrate large particles in protoplanetary disk. So once you're a Stokes number 1 particles, this is really where you want to go to any of these regions that are highlighted here. Let me just go through them quickly. I have the references for you down here if you're interested. In the inner part of the protoplanetary disk, you're probably MRI active, and you have the MRI pressure bombs, which I talked about. Then we have the dead zone here from maybe a half to 40 AU, a half to 30 AU, and the dead zone edges are associated with pressure gradients also. The inner one can directly trap particles, the other one cannot trap particles because the pressure gradient goes the wrong way, but it can become unstable by a Rossby wave instability, and then these vortices which form can actually then concentrate particles. Then inside of the dead zone, we can have the streaming instability working directly because there's very little stirring inside of the dead zone. We can have the baroclitic instability, which can make vortices. We can have even at the ice line, there can be a increase in the ionization, which makes a pressure bomb at the ice line. We can have a planet, which makes a gap, and a pressure bomb at the outside. And when we go out of the dead zone again, then we have the MRI active regions out here with the pressure bombs, and even out beyond 100 AU, but the disk may be gravitationally unstable. One can have self-gravitating spiral arms, and then these can also trap large particles. So it's very space-filling, the area in which Stokes number 1 particles actually get concentrated. Let me go quickly back to the streaming instability actually, and show what happens when we include the gravity between the particles. I'm going to show a movie of this also. Just want to highlight this plot here first. It shows as a function of time, the maximum particle density that we reach by the streaming instability without any gravity. And just focus on the yellow line for now. We see at a low resolution, we go up to 1,000 times the dust-to-gas ratio. At a moderate resolution, at 4,000. And at a high resolution, we even go up to 10,000 times the local dust-to-gas ratio. Again, extremely high concentrations there. And of course, these concentrations are gravitationally unstable. This is just showing the effect of the metallicity, 0.01, 0.02, 0.03. At 0.01, in a space-time plot, we have almost no concentrations. But at 0.02, we start having strong concentrations. And at 0.03, we have really, really strong concentrations. Let me show you a movie of this, what happens when we turn on the gravity between these particles. It's a rather long movie, so I'm not going to show it all. Okay, so this is just the beginning of the movie. We see the disk from the top here. It's a local co-rotating box. We see from the side here, the stars in here somewhere. We see that the particle becomes turbulence, the particle sediment to the midplane here. We have here a metallicity of 0.01. And basically, we are going to get a midplane layer now here, which is stirred up and doesn't have any strong clumping, and therefore doesn't form any planetesimals. So I'm going to skip a little bit ahead in this movie, and I'm going to show you what happens when we increase the metallicity now to 0.02. So we're going to remove half of the gas, because nothing happens at 0.01. And then I'm actually going to skip a little bit further ahead, like here. And then I'm going to show you these filaments which form. So here we get a dense filament forming by the streaming instability. Here you see it from the side. Let me just move this one here. And now as the filament forms, it also turns into planetesimals. A lot of these areas becomes very dense. It makes planetesimals here. You can see their hill radii here. They are very close together. And here you see as a function of time, you see their particle radii that they are approximately between 50 and 200 kilometers in size. Yeah. So we get a range of sizes from approximately 50 to 200 kilometers. And if you want to know more about the streaming instability, I invite you to look at the posters by Xiaotian Yang or by Tetsu Taki, who have more information about the streaming instability. Right. Okay. Now one has to be a little bit careful here about associating the clumps that form in these simulations with planetesimals. And the issue is, we don't know if there's a one-to-one match between a clump, which is about to collapse to a planetesimal, and the planetesimals which form. You could, in fact, form many planetesimals and not just one. This is an example of the clump mass function, so to say. We can measure the dn/dm of the clumps, and we see it goes approximately to m to -1, a paper in preparation, so very dominated by the largest clumps. The larger clumps are few, but are much more massive. So most of the mass goes into the large clumps. But this is formally only the initial mass function of pebble clumps at the grid scale. We don't resolve what goes on all the way down to planetesimal sizes. Actually, what we should include are sticking and bouncing, erosion, fragmentation, all kinds of physical collision effects that will then determine the further collapse to planetesimals of a range of sizes. And this kind of investigation was actually pioneered by Nesvorny in 2010, who took a pebble clump, so to say, from one of these simulations and involved it in a separate n-body simulation. And then basically saw the pebble clump collapse on its own weight to form not one planetesimal, but form a binary. And this is very interesting because there are many binaries in the Kuiper belt, of course. Nesvorny had to assume pure sticking between the particles, a very pioneering work here. And of course, what you want to do in the future is you want to include all of these different coagulation, fragmentation, erosion effects inside of these dense clumps. That's a completely unexplored venue for collision physics. And if you want to know more about that, I invite you to see the posters by Carl Johansen and by Mutashi Bukhari. Okay, yeah, good. Now, according to the very last part of the talk, where I'll be so bold as to propose a unified model of planetesimal formation, which relies both on coagulation and on gravitational, and on particle concentration and on the gravitational collapse. I'm not going to talk about comet nuclei because I don't have time, but we think that there's evidence that even small comet nuclei may actually form by a gravitational collapse of millimeter, centimeter-sized particles. This is a paper by Skoroff and Bloom, which I invite you to look at, and we will also have this in the review. But I'm just going to come to my concluding slide here and basically propose this unified model of planetesimal formation. Because if you look at all of these three effects which I talked about, the mass transfer and high-speed collisions is very efficient, but it's also very slow, particularly in the outer part of the disk. It cannot compete with the radial drift or with the disk dispersal. Yeah? On the other hand, you can grow very fluffy ice aggregates that have very high cross-sections and grow to very large sizes, but it's still kind of unknown how they compactify and what about the erosion by the gas. It's not entirely known how these particles would survive the gas flow around. Finally, we have the particle concentration and gravitational collapse, which formally I would claim has no growth barriers, because once the particles become gravitationally bound, they have to find each other somehow. So even though there are boundary barriers and so on, the particles have to get around it somehow if they're bound to each other. But it requires the prior formation of Stokes 0.1 to 10 particles. So there's been a lot of discussion in the literature over the last 4 decades or something, whether planetesimals formed by coagulation or cell gravity. But actually, one thing that we hope that our paper will be cited for in the future is for saying that planetesimal formed by coagulation and cell gravity, because there's no reason to distinguish between those two effects, basically. So we basically propose a 4-phase model of planetesimal formation, where we have in the initial phase, we have the growth of fluffy aggregates. And then in phase number 2, either you get compactification and mass transfer, such as here, or you get the continued growth of fluffy aggregates. But under all circumstances, when you come to phase 3, and the particles grow to approximately Stokes number 1, then they concentrate in pressure bumps and vortices and by streaming instability. And then finally, you have a gravitational collapse that yields the planetesimal initial mass function, which could be binaries, could be large dwarf planets such as Ceres and Pluto, and could even be these small comet nuclei. And what's important to note about this unified model is that coagulation plays an important role in all of these phases, particularly also phase 4, where the interaction between the particles is what will eventually set the initial mass function. So with that, thank you for your attention.
Yeah, thank you, Anders, for this very nice overview. The talk is open to questions. Jan, please.
Yeah. It's work, yeah. Just if you look at your plot, your fluffy aggregate, they don't look very spherical. So what do we know about gas drag laws for very fluffy aggregates that could have holes and things like this? And do you think it's important for the simulations?
Okay, the Carlo should really answer this, but I think I think the answer is no. We don't know a lot. I think one issue is that you could assume that there was a nice Stokes flow around, a laminar Stokes flow, but if it's very fluffy and have a lot of structure, you can get turbulence just by the flow around. So my impression is that this is simply not known. It's something that people will have to do in the future.
One remark, please. So don't worry about this photographer here. He's just checking how many are here and how many are awake and so on. So please don't worry. So next one, Roman. No.
Roman Rafikov, Princeton. I have a question about this gravitational excitation of small particle velocities. I would expect that unlike turbulent velocity fluctuations, which are predominantly small scale, this would be large scale perturbations which have scales comparable to the scale height of the disk. And then when you talk about collisions of two small particles, on these scales, they basically feel the same gravitational field, so their relative velocity will probably be affected much less by the gravitational perturbations than their absolute velocities. And in that sense, I wouldn't expect gravitational perturbations to be as effective. This is totally different for big bodies, which are decoupled from the gas.
Sure.
And then you indeed get a strong excitation.
I
But
agree.
for these particles, with millimeter sizes, that probably is not going to
No,
happen.
no, these small ones are actually excited by direct gas drag. This plot is including both the direct gas drag here, which goes down, and then you get the gravitational.
Well, so that's what surprises me, that they are so effective at doing this.
At these sizes or at these sizes? At the large sizes?
At small sizes.
But the small sizes, this is the direct aerodynamic drag which goes around.
So no, that's what I'm saying, that gravitational excitation is probably not relevant for this
No,
small
it's not relevant
particles.
at all, but that's why. This is the gravitational excitation part,
Oh,
and
sure,
this
sure,
is
sure.
the
Yeah,
direct
yeah. At
gas
larger
part.
sizes,
And
that's
it's not
fine,
important at all for the small particles.
Okay, I
No.
think we need to come to the next question. Gerhard, no?
Gerhard Wurm, Duisburg. So if you do this scenario initially, you have all the mass you need on solids in the disk. But initially you said that, for example, chondrules form over 3 million years. So you also need to make asteroids after 3 million years from scratch.
Yeah.
Do you still have the densities to do this by instabilities?
Well, I think chondrules is a particularly tricky situation, which we don't really understand what the role of chondrules is for planetesimal formation. One thing you could imagine is, for example, that you form a very early generation of differentiated meteorite parent bodies, and the chondrules are then flying around, and then they're actually accreted by these parent bodies over the next millions of years. So in that perspective, it's possible maybe that the primitive parent bodies have, so to say, a core of a differentiated one with a huge mantle of primitive material around. That's one way to have chondrules flying around for several million years, because this accretion process would be extremely inefficient. So I think that's one way you could imagine it to happen. Another way, if you look at the streaming instability, it needs to go above a certain threshold. Every time you kind of take planetesimals out of the streaming instability and you get less mass in the pebbles, when it goes down to a metallicity below a metallicity of 0.01, you immediately release these particle concentration filaments, and then the particles could go out again. So it's also a possibility that the streaming instability is a very kind of sporadic effect that happens sometimes, somewhere, and then the rest of the time you just accrete unbound pebbles.
Okay, in the middle here, Peter.
Peter Wodkes at Andrews University. My question is, wouldn't that have any observational consequences in the SEDs or images? Because when you change the particle properties so dramatically, or is it that maybe everything is actually taking place in a hidden midplane where you just can't see them?
You're talking about the fluffy particles.
Yeah, I mean, all these dramatic changes in the size distribution you have talked about, the extreme fluffy aggregates.
I think the idea of the fluffy aggregates, as far as I understand, and Hidekazu should correct me if I'm wrong here, is that it's just a temporary thing. It is on the way to becoming a planetesimal, and they will actually compactify when they go up to kilometer sizes and then become compact again. So I don't think the idea is that there should be a lot of fluffy aggregates flying around, but there should be a kind of an in-between stage. I think if you talk about in general what you see from protoplanets of this world, you see lots of emission from millimeter, centimeter-sized pebbles, right? And I think this is in perfect agreement with these kind of models where the pebbles are really the ones that are undergoing planetesimal formation. So I think this is in agreement.
Okay, time for a few short questions and short answers. Andras now first.
Is it working?
No, now.
Okay.
Yeah.
Okay, this is Fredrik Weinmark from Heidelberg.
Oh, Fredrik.
So I have a couple of questions, comments regarding the mass transfer and sweep-up scenario.
Okay.
So what I just want to point out is that it is possible actually to... Okay, yes. So it is possible actually to form these first seeds for sweep-up just naturally by including velocity distributions, for example.
Right.
And it was also recently shown by Joanna Draskowska that it's possible to form them by radial mixing.
Right.
And the second point I want to make is that C et al. From 2011 showed that it's possible in this type of scenario to actually grow planetesimals of tens of kilometers in size by pure sweep up. And it just has to do with the different disk models or collision parameters that you use. So you can definitely go big.
No, sure, there are probably other ways to make planetesimals also, yeah.
Maury, please.
Yeah, I like your story, as you know, except the part on fluffy particles. And the reason is that when you open a meteorite, so what we actually know about the planetesimals, in particular ordinary chondrites, you see that they are collections of chondrules, or hard spheres, with almost no matrix among them.
Yeah.
So I can't imagine the fluffy counterpart of their precursors. Can you comment on that?
No, I think, okay, if you look inside of the meteorites, you see so much stuff that's thermally processed, and I think this is still such a big mystery in a way. We don't highlight anything here that could lead to any thermal processing. I think when it comes to the fluffy aggregates, I don't know if Hidekazu or Akimasa or someone will go. Hidekazu, do you want to say something to this?
We are thinking of the fluffy aggregate. It's an icy aggregate. So I think it's chondrule formation is like after the planetesimal formation, due to the collision like that.
Right.
Then we can resolve your problem. Okay.
Okay, please.
Is there a typical size that we can take away from the initial planetesimal mass function? Like people say the streaming instability makes particles that are born big. What is that typical size?
Well, this is what I'm showing here. This is basically some work in progress. It shows you basically, so how should we interpret this? As long as the mass, this is approximately 200 kilometers, this is 100 kilometers. It shows that dm goes down as maybe 1 over m. And that means in terms that if you multiply this by m and you look at logarithmic bins, then you get much more mass in the largest bodies. So it's a fairly shallow size distribution that puts a lot of mass in 200, 300 kilometer size bodies, but also it actually puts most of the number in the smallest bodies. And we don't know how low we can go. We know that we can go down to approximately 100 kilometers here, but when we go to higher and higher resolution, we go more and more down this line here. So it could be that it extends all the way down to kilometer sizes. We don't know that yet.
Thank you.
Okay, last question to Ralph.
Yes, could you put a time scale on this? When can we expect planetesimals to appear in these disks?
From my point of view, the minute you can form pebbles. The minute you can form centimeter, millimeter sized pebbles, there are so many ways now to concentrate these particles. And the concentration phase and the collapse phase is so rapid, a few 10 years, a few 100 years maybe. So I would say this is all set by the pebble formation time.
What is your prediction for that time then?
It's around 10 to 4, 10 to 5 years, depending on where you are in the disk. If you're at 100 AU, obviously it takes a lot longer time, right? And if you're in the inner part, it takes shorter time. But between 10 to 3, 10 to 4, 10 to 5 years, something like this.
Okay, let's thank the speaker again. Anders, thank you.